And so we are asked to find the heat of combustion of ethene in pure oxygen. And so that's assuming it goes to complete combustion. We produce carbon dioxide and water as a result. We're going to be using bond energies to make this calculation. And so what matters is the kind of bonds that are involved. And so what are the two elements that the bonds are connecting, and whether they're double bonds or single bonds or not, as well as the number of those bonds that are involved. And so ethene is the molecule. It's a gas that's released by bananas. Well, it's released by a lot of things, but bananas are the primary example. And it's also a plant growth hormone. And so if you put a banana in a paper bag with plums or something that you want to ripen, the bananas release this ethene, and that acts as a ripening agent for the other fruit. Now, if you look at ethene, basically you've got 4 carbon-hydrogen bonds. Each carbon-hydrogen bond has 413 kilojoules per mole of bonds, and we have 4 of them. And so that's the first part of the equation. That's the reactant side. What needs to happen? I need to invest energy in tearing those bonds apart. Once I invest that energy, then I have to break carbon-carbon double bonds, and so I have to invest energy to do that. And finally, I'm going to need 3 oxygens, and so I have to break 3 oxygen-oxygen double bonds. I need to invest that energy as well. Now I can consider my product side. This is where we're going to be gaining energy, because as we bring the atoms together, as the bonds are made, there will be a release of potential energy, and that will be released in the form of heat. So once again, all I really need to do is consider the types of bonds that are involved, as well as the number and the energy involved in creating a mole of those bonds. And so we're going to be making 2 carbon dioxide molecules. And so you'll notice there are 4 double bonds there. And we are also going to be making 2 water molecules. And so there are 4 oxygen-hydrogen single bonds involved in that. And so when I'm done the entire calculation, I take all the energy that was involved in breaking the bonds, in other words, all the energy I had to put into the system, and so that becomes a positive here. I subtract out all of the energy that gets released from the system, and that's why this is negative. It's because it's leaving the system, and then when I add them together, I get 1,312 kilojoules for every mole of ethene that gets burned. And so that is how we find the energy based on a bond energy approach. It's not perfect, but it's close.